Okay, so let's do an example of a cosecant. Now, here's the way we're going to approach this. We're going to pretend for just a minute that it's a sine curve. We're going to pretend it's a sine curve. So the first thing you do is you look at it and say, okay, so A is 4. So that's pretty normal. B is 2, which means the period, formula is still the same for period. The period is still 2 pi over B. So 2 pi over 2. So the period's pi. The phase shift is going to be negative pi over 4, the 0 of the x part of the problem. So the phase shift is negative pi over 4. And like we keep emphasizing, or at least I keep emphasizing, that becomes the new center of the graph. And me, just being a nerd, I like to say, okay, I'm going to write that on there right now in the center of the graph so I don't forget it later. So that is my new vertical center of the graph. That's my new vertical center of the graph. So I've got it written on there. The displacement, you can say it's up 2 or just 2, which means your center line is y equals 2. So we can label this guy y equals 2. Now, the equation of the asymptotes is going to be a big deal. That's going to be a new thing. So we're going to talk about that. That is a big deal for these problems. So the first thing is, okay, we're pretending it's a sine curve. Okay, no big deal. So we do it the same old, same old. We say, okay, if my center is at negative pi over 4 and I got to move pi spaces, my period is pi. So that endpoint is 3 pi over 4. My endpoint down here is negative 5 pi over 4. That goes to the whole, I subtracted pi. Got to start cutting these guys in half. So that's a negative 3 pi over 4. Cut this guy in half, halfway between negative pi. Well, that'd be pi over 4. Fortunately, these work out pretty nice and neat. So that's pi over 2, negative pi over 2, negative pi. So there you go. You got your labels, just like we always want. Okay. And we're always going to have, and like I've said, this is going to be the tricky part of all these problems. Always coming up with the it's not the x-axis, it's the horizontal axis, labeling the horizontal axis. All right, we're still pretending it's a sine curve. So let me see. My center's at 2, but my A is 4, so it's going to go up 4 spaces. So it's going to go up to 6 and down to negative 2. And then you say, okay, it's a positive out front, positive sign. So we go, I'm at the center. So I go up to the max, down to the min. I'm sorry, down to the center, down to the min, back to the center. So I'm going to graph the sine curve, but I'm going to make it in dots. So here's the sine curve. Here's the sine curve that I would be using right now. If this was a sine equation, this is what we'd have. All right, now for the fun part. If that's the sine curve, now we're going to graph the cosecant curve. Well, like we said in the example, every time the sine curve crossed the center line, that's when it didn't exist. And somebody says, I don't believe that. That's too easy. That didn't work. Okay, well, let's check it out. It's crossing the center line right there at negative pi over 4. If I put negative pi over 4 in there, that makes 0. 2 times 0 is 0. And cosecant of 0 is undefined. What do you know? So at negative pi over 4, it didn't exist. So everywhere that the sine curve crosses the center line, the cosecant curve does not exist. Thus, that becomes the asymptotes. And that is when I use dashed lines for asymptotes. Okay, so those are my asymptotes. And that's going to be, writing the equations is going to be a little different here in just a second. Then you can say, okay, no big deal. because now we can graph the whole thing. You can say, all right. Remember how we said, oh, so basically when you graph them, the sine curve and the cosecant curve have that max min in common, and then they just flip over. And then it just flips over inside the asymptotes. So they have that max min point in common. It just flips over inside the asymptotes. They have that max min in common. It just flips over inside the asymptotes. Have that max min in common. It just flips over inside the asymptotes. Just like that. Now, here's where it might get a little bit goofy. Amplitude's easy. Amplitude's easy. You'd say, oh, let me see. Here's the curve. It's down here at negative infinity up to -2. Then there's a gap. Starts over at 6 to positive infinity. I'm sorry, that was the range. What I just said was the range. Negative infinity to -2. And then 6 to infinity. That was the range. Amplitude. Now, remember how we said amplitude was the distance between the center line and the max. Center line, well, in this case, center line and max that's going to go up to infinity. This is going to go down to negative infinity. So basically for amplitude, for secant, cosecant, secant, cosecant, and then also for tan and cotan, we're going to end up saying they're going to have no amplitude. And I think on the test and quiz, we don't even ask you for the amplitude on these problems just because they get extra tricky. So we're not gonna even do that. All right, now here's where it gets a little fun. The equation for the asymptotes. Equation for the asymptotes. All right. So you're thinking, okay, well, how am I supposed to come up with some general equation for every one of these asymptotes? Okay, well, it's really not that hard. All right. We're going to use this general form all the time. We're going to say x equals, because they're vertical lines. They're vertical lines, so vertical lines are always x equals, okay? What you do is you just pick any asymptote off the graph. Pick any asymptote off the graph. So like I would just pick the easiest one, that -π/4 right there. That's right in the center. So my equation of the asymptote is going to be x equals -π/4. We're not done yet. Plus. All right. There's an asymptote every, let me see, from -π/4 to π/4. Let me see, that's π/2 spaces. From π/4 to 3π/4, oh, that's π/2 spaces. From negative pi, oh, that's π/2 spaces. Oh, from the, oh, so it looks like the distance between the asymptotes is always π/2 spaces. Well, how convenient, π/2 happens to be half the period. There's basically an asymptote every half a period. Well, that's our formula then. We're going to have an asymptote every half a period. And then well, how are we going to symbolize that? Because this was 1 times half a period. 2, how do we symbolize we've got different, the different ones? Well, what we're going to do is we're going to use the letter N. And when we use the letter N, most of the time in upper level math class and formulas, when we use the letter N, it stands for integer. Okay, so if I say N times and I want half the period, so basically the period over 2. So that's our asymptote formula from now on. N standing for integer. Pick any asymptote, N times half the period. Well, our period was pi, so N times π/2. And there's your asymptote formula right there. Okay. Oh, and then last thing, I always forget this myself. Last thing, let's put the y-axis on there. Last thing. And by the way, you'll notice we didn't ask you the domain on this, because of the domain, you'd say, well, I just have to chop it all up. I'd have to write this to this union, this to this union, blah, blah. And that's just kind of silly, making you write that over and over. Or you could say, well, the domain is everything but the asymptotes. Well, you're already writing the equation of the asymptote, so we don't really need to do that again. So we'll leave that off. All right, so I will do an example of a secant graph next. That'll be another video.